Hello everyone. My name is Siyoung, and I'm a technical education manager for databases at AWS. I'll be your host and moderator for this workshop series. This is the fourth episode of the 5-week Getting Started on Amazon DynamoDB virtual workshop. We are broadcasting live from Seattle from our home offices, but we'd like to thank you for being here with us throughout all of these series and making it a success. Also, we will try our best to address all of your questions through both chat and voice, so be sure to use the chat window to ask your questions. In today's episode, we'll be building upon what we've learned in the previous ones and discuss how to create a DynamoDB table for a social mobile app as an example, and also to learn how to model your tables using the single table approach, using secondary indexes and even transactions. So now I'll hand over to Pete, our expert on NoSQL databases. Pete, the floor is yours.
Hey everybody. Yeah, thanks for the introduction. My name is Pete Naylor. I'm a specialist solution architect for DynamoDB, and I've been with AWS almost 4 years now. Spent the first 2 years as part of the team that supports Amazon.com as a customer of AWS, and worked on a lot of large database migrations with them. Got to really like DynamoDB, and then moved into this role where I'm working a lot more with external customers and helping them to adopt and migrate into DynamoDB. So looking forward to this particular session. We've had a series of 3 already. This is our 4th, and we're going to do a lot of similar things to what we did in last week's session. I think maybe practice is a good thing when you're learning how to do data modeling. But we'll dig a little bit deeper on transactions, and we'll be using a different scenario, a different use case. So in this use case, we're talking about, as Siyoung said, a mobile app for kind of a social network that's built on photo sharing. So the first thing that I like to do is to think about an entity relationship diagram, mapping out the various entities, the relationships between them, the kinds of attributes that we want to have on each item, the things that we want to keep track of, similar to columns in a relational database. And then to think about whether they are one-to-one relationships, one-to-many, or many-to-many, and just kind of get a feel for our first iteration that we want.
Let me try to answer a few questions in the chat. So there's a question from Narsimha on when will time series DB be available. So it is already available. We have a time series database called Amazon Time Stream. It's in preview right now, but it's you can sign up and actually play with it. And another question is, how does DynamoDB compare to MS SQL or SQL DBs for volume handling? I'm going to have to rely on Pete for that question. Oh, it looks like Pete is back. So Pete, I was just doing my little dance while you were rebooting your laptop, but the floor is yours again.
All right, thank you. And maybe you could mark that question for us to come back to in just a little bit. I think I was probably just saying, I'm not quite sure where we were when I cut out, but with this particular entity relationship diagram, where we've kind of got a rough idea of our entities, relationships, attributes, and maybe starting to think about where we can make use of DynamoDB's collections. So using a set of items that have the same partition key but a different sort key to build one-to-many relationships. So the next thing we want to do is really think about our access patterns. And we can break this down across the various different users or different parts of the application. The first is that we're going to have user profiles. So we need to be able to create a user profile, update user profiles, and get that user profile. For our photos, we need to be able to upload a photo. We need to be able to view the recent photos for a particular user. We want to be able to react to a particular photo. And then we want to be able to view an individual photo along with its reactions. So how many smileys it's got and how many thumbs ups and so forth. We also have a need to model friendships, and this is probably, we can already be thinking that this is probably something that will wind up being a collection, a one-to-many kind of a model. We want to be able to follow a user. We want to be able to view the followers for a particular user, and we want to see who someone is following, so who is followed by a particular user. So coming back to what we touched on last week, what we want to do when we're building these data models with DynamoDB is first we want to denormalize where we can and where it makes sense. And what I mean by denormalizing is in a traditional relational database, we might map out a unique table for each type of entity. And we have a particular schema for every item in that particular table. We have a set number of columns, and all of those will be present for every item. In DynamoDB, we have schema flexibility, so we can have a different set of columns or attributes for every item in the table. And what we want to do in denormalizing is, instead of using a traditional join from a relational database, we want to kind of do all the joining ahead of time and store the item with everything we need to know about it, so we can make a single request and not need to be making joins on the fly. The other thing we want to do is to build collections. And again, when I talk about collections, a collection is the set of items in a DynamoDB table or index that have the same partition key value but a different sort key. So it's kind of like a bucket or a set of things. It collects up a number of different items and says that these are related by that particular partition key. We want to make sure that we're building support for our primary patterns into the tables themselves. One of the reasons being that in a table we can have strong consistency, we can do reads and writes in the table, and we want to then carry our secondary patterns for queries for reads out of global secondary indexes. And so we have this kind of an art, I guess, a set of different things to keep in mind as we're approaching this model. The last thing that's going to happen is that we're going to have to iterate. This is not unusual at all. You take a first look at a particular use case, and you can start with a data model. Very often, as you start building, you think, no, I really want to go back and change that a little bit. So one of the great things that we have to help with this data modeling is a tool called the NoSQL Workbench for DynamoDB. It's generally available now. You can go download that for free, and it's a standalone application that runs on Windows or Mac, where you can kind of describe your schema. And one thing to keep in mind is while DynamoDB doesn't have a fixed schema, it does have a schema. It's just controlled by your application. You decide what attributes, which columns each particular item will have. So you're going to have that concept in your mind. You're going to already think about different entities. You're going to track different values, different attributes, and you can build that out in the NoSQL Workbench. So what I'm going to do is just quickly show you. I'm going to switch to screen share. I can show you the attempt that I first took on this particular model, so that we can build on that through this example. All right. So here's the NoSQL Workbench. Again, we have three different areas to the workbench today. First is this data model. And you can see that I created a table definition. I said that for our single table, we're going to call it Quick Photos, and the partition key will just be called PK, and the sort key will be SK. And the reason we use something generic like that is, in this particular table, we're going to have a number of different types of entities. And so the value that's stored in that PK or SK attribute could represent a number of different things. So it doesn't really make sense to call it one particular thing. We'll stay flexible on that. I also created a number of the other attributes that we'll need, and obviously each of these types of items might have a number of different other attributes, but I'm really just sticking for right now with the attributes that I know I'll want to use as part of our index. The other attributes are optional in every record, so I didn't worry about that. Once we've created this data model, we can go to the visualizer, and in the visualizer we can add some example items and entries. So you can see that if I take this aggregate view of the table itself, I'm using a partition key of just PK, and I have a number of different items in here. We have some user entries and also some reactions, and I'm going to collect up friend records and some metadata about the particular user in addition to any photos that they've uploaded in one collection, so they all have the same partition key value. You can see we have user C. Young and user Pete. User C. Young is friends with Pete, and Pete has also set up a friendship with C. Young. We have metadata that includes some other information about the user profile itself. And then we also have reactions. So in this case, we've decided to use a partition key that says this is a reaction. We use a prefix to help us maintain uniqueness there. The user who reacted is Pete, and the type of reaction was a smiley. And so then we can say that the reaction is related to this particular photo. So we can also build global secondary indexes, and we'll see why we're building this index later. But here you can see that we've basically swapped the sort key and the partition key values. This allows us to query the other direction when we need to. So I added some hopefully enlarged views of this so people can see that. Again, you can see the example entries that we've put in here. And putting this example data in helps us to visualize how well our first attempt at our data model is going to work. Does it cover the different use cases and the query patterns that we already outlined are the ones that we'll need? We may have to come back and iterate on this. We can change our data model if we need to, as we find out that maybe we forgot about one particular access pattern when we were making our list. In which case we'll come back and just iterate on the design until we get exactly what we need. So,
Pete, there was a number of questions on the data modeler. Is this something that the attendees can download somewhere? The data model itself. Yeah.
Oh, the data model itself. So I did not actually save this out, although I can. What you can do is go and download the actual example itself, and from there we can develop the data model. I think I may be able to actually just save this out, and I can probably provide it along with the information that we email out after the session. So hopefully that will be helpful. Okay, so again, here's our view of the GSI that we're going to use, the Global Secondary Index. So one thing I wanted to touch on just before we dive in any deeper on this particular data model and this workshop example that we're going to work through, I want to talk about ACID compliance or ACID properties, and many people have probably heard that, maybe didn't necessarily put a lot of thought into what it meant. It's something that these properties are things that are important when you're using a database that's transactional in nature. It's operational. You want to be able to have some guarantees, including atomicity, consistency, isolation, and durability. So I'm going to just kind of touch on each of those in DynamoDB context, first for a single item, and then we'll move on to some other more complex requirements. The first I wanted to touch on, of course, is durability, and I'm doing these out of order, I know, but durability is one thing that we get automatically with DynamoDB. We know that when we put an item into DynamoDB or when we make an update, that is durably stored in 3 different AZs. So we maintain that data for you. It is a durable and persistent data store. The second one is consistency. And this one's a good one to touch on because I think many people who haven't worked much with NoSQL databases make an assumption that NoSQL databases can't provide consistency. And what I mean by consistency is read after write consistency. So when you make an update to an item and you change a particular attribute value, if you immediately come back and read that item, will your read encapsulate all of the writes that have been made up until that point? And I think, going back on some other NoSQL databases, it was difficult to get guarantees around consistency. With DynamoDB, we give you the option on every read call to choose whether you want a strongly consistent or an eventually consistent read. And the eventually consistent read is the default value throughout the SDKs. Many different use cases work fine with eventual consistency. And from the DynamoDB infrastructure perspective, it allows us to scale and use our infrastructure more effectively. So an eventually consistent read is actually discounted by 50%. It consumes half as much read capacity. So the recommendation there is to use eventual consistency by default. And then when you think in your application and in your workflow, you really do need strong consistency, then you have that option. And that's true for every single read. You get to make a choice each time. It's not something you have to make a choice on when you create the table. So it's a really nice, flexible thing to have. When you make a write into DynamoDB, you won't receive a response confirming that it was committed until it has been written to at least 2 of the 3 copies of your data. And when you come back and you say you want a strongly consistent read, we will make sure that that read comes from one of the up-to-date storage nodes. So that's consistency. The next one is isolation, and isolation is more like locking. There's a couple of different ways to do locking. One of them is pessimistic, where you lock an item and then nothing else can change that item until you unlock it effectively. That can be a little problematic when you get to really high throughput and high concurrency. Another pattern would be optimistic locking. And DynamoDB for any single item has always supported optimistic locking through a pattern that we call multi-version concurrency control. So what we do is we can make, every time we make a write, we can specify that write with a condition. So we can say, for this particular write, I only want you to actually commit it and make the write for me if this requirement is true. Oftentimes that pattern would be in a particular item, we're going to store an attribute that says this is the version of this item. So we're going to use a pattern from the application side where we do a read, mutate, and then conditionally write back to that item. We would read the item as it existed. We'll see the version that it's currently at. And then in our application, we will make our changes, calculate whatever we want to do. And when we go back to update that record, we're going to set the condition that says, I only want you to commit these changes, this new view of my item, if the version is still what I thought it was when I read it. If it fails, then we kind of repeat the whole process. We get the new view of the item, we make our our mutation, and then we conditionally write. So we can actually have isolation optimistic locking in DynamoDB using those conditional writes. The last one is Atomicity, and Atomicity really means when I make this change, I want it to be all or nothing. And that's really pretty easy when we're talking about a single item in DynamoDB. It's important to recognize that when we denormalize it and it has everything we need in it, any change we make to that item is atomic. It's either going to update the entire view of that item or not. So the interesting thing about DynamoDB is, as an operational database, as an online transactional processing database, it has already always had these properties for a single item view. In November of 2018, we introduced transactions, and these are for multi-item transactions. They allow us to, again, we still have durability, we can still make consistent reads, we can even now, using transact get items, say, I want you to read these 5 items, and the items could be across multiple tables. They have to be in the same region and AWS account. But you can make this transactional get and say, I want a picture of these 5 items as they looked all at the same time. So it's consistent across a number of different items. We still have isolation because we can place locking, and transactions are serial in nature. We can't have one transaction conflicting with another. Only one of them can be in progress at the same time. We have atomicity now across multiple items in multiple tables. So we could make a write items call, which updates up to 25 different items that could be in 25 different tables. Does this mean that we really want to go back to a third normal form, or a normalized model where we keep 10 different tables for the 10 different kinds of items, and we want to go and join on those, effectively building our own relational database engine in our application? No, we want to, if we can simplify, if we can denormalize that item, we don't need transactions. We can use DynamoDB's inherent single item properties. So transactions is a really nice tool that allows us to support some more complex workflows. You'll see through the workshop that we'll make use of that to provide additional guarantees across multiple items. And the last thing that the transactions APIs that we added offer us is idempotency, which is another really important feature, I think. Idempotency means if I was to repeat this same request or this same operation multiple times, would the end result still be the same? So if you can imagine in DynamoDB context, we're not making a connection that stays in progress for a long time, and we open a transaction, we do a number of different things, and sometime later we decide to close the transaction. DynamoDB is using a RESTful web interface. So we make a request and we want that response almost right away in very low latency. So what happens if we make that request and we want to make a change and mutate a particular item? If our application process dies for some reason, or there's some kind of a network issue where the response from DynamoDB doesn't make it back, we now don't know whether that change was committed or not. And so idempotency is a really important thing. We want to understand, should we retry it, or has it actually already been committed? With the transact write items API, we're able to provide a idempotency token which says, if you see this same token in another request with the same parameters again, reject it. Don't recommit that same change. And in that way, we can get idempotency across some fairly complex operations. So a really, really interesting feature, I think, of transact write items, and I'm seeing some really nice and more complex data models developed around transactional APIs and using that idempotency token. So I did want to touch on that because we are actually going to use some transactions later in the workshop today. And so with that, I think I will go ahead and let's get started on the workshop. We lost some time when I had to reboot. So hopefully everybody has a AWS account that they can work with. We will make use of that. First, we want to log into our console, of course. And we're going to set up a Cloud9 environment where we can run some scripts and do some work against DynamoDB. We can type that in here and find our Cloud9 section of the console. And what we're going to do is create our environment. I'm going to call this environment Quick Photos, and you can choose whatever environment name you like. Maybe I'll put a description that says DynamoDB Workshop. I'm going to continue to the next step. And all of the defaults here are actually fine as they stand. What's going to happen is that Cloud9 will spin up an EC2 instance for us. The smallest instance type is fine. It's free tier eligible. So we'll go ahead and choose, we'll go with all of the defaults here. It's good to see that after 30 minutes of inactivity, it will actually hibernate that instance for us. So that's a pretty cool feature, I think. All of the defaults are fine. So we will go ahead. It's going to ask us to confirm that. Oops. There we go. So let's go back to see if we can answer some questions. That's going to take a couple of minutes to spin up. Let's see. Young, do you have some questions that I should take a look at?
Yeah, I assigned a few to you, so just take a look at those first.
Here's one from Ted. How does DynamoDB compare to MS SQL or SQL databases for volume handling? And I think in this, I think what you're talking about in volume handling is maybe the number of requests per second or potentially the amount of data that is stored. Either way, the nice thing about DynamoDB is it essentially builds in horizontal scaling right from the start, and it takes care of all of that for us. So no matter how much data you want to store in DynamoDB, we have customers with petabyte scale tables. We can scale that out horizontally as far as we need to go. And in doing so, as we scale out horizontally, we actually increase our ability to handle higher throughput, more requests per second. The important thing to remember is we use that partition key to help assign or to distribute our data and our traffic across all of those nodes on the back end. So choosing a partition key is very important. You want to choose a partition key that gives us high cardinality, so a lot of unique values. And we want something that will grow in number of values as our use case grows. One example might be a user ID would be good. One that maybe seems at first to be a great idea that perhaps isn't would be choosing a US zip code, for example. If we start with a number of different users, everything seems fine. It seems like there's lots of different values of zip code. But what if we get into the millions of customers or users? We're going to find that at some point the zip code count doesn't keep increasing, so we're not able to scale out with the number of users and the traffic that we need to carry. The other thing that's perhaps not so good about using a zip code, or something to remember, is that some zip codes are going to be very much busier than others. Some zip codes have a lot more people in them. So that's a basic comparison, I guess. Traditional SQL and relational databases can build answers for us on the fly by consuming memory and CPU. It doesn't necessarily decouple that from the storage and the amount of traffic we have. So it's flexible about being able to answer questions we never thought we were going to have to answer. There are some performance trade-offs with that. DynamoDB is really much better where you know what your questions are going to be of your data, and so you're kind of going to pre-build all of the answers and store them so that when you ask that question, you can go grab it immediately. And you may find in your use case you decide there's some new question you need to be able to answer, and that's where we can build in a secondary index. So that's kind of the difference between the two. See if I can find one more question. In a scenario with one table database model, is it possible to use data from that table as a data source in the AWS QuickSight for BI and have all benefits for drill down as we have with relational database and joins within? You know what? I don't know the answer to that one. To be honest, I'm not a QuickSight expert, so I might have to pass on that one for the moment.
My understanding is DynamoDB does not provide native integration with QuickSight, one option is to import the data using data pipeline into EMR. And from EMR, you can use QuickSight to process data for analytics. But it's not a direct plug-and-play scenario.
Great. All right. Thanks, Young. So I'm going to go back to sharing my screen because my Cloud9 environment is ready to go. Hopefully everybody can see that. In Cloud9 we have firstly our listing of files over here that are on our instance in our environment. We have a window up here where we can view and edit our code, and down here is where we can see the results of actually running that code. One of the tabs here is a shell that we're going to use to actually go and grab the code that we're going to work with. And I think Young is going to paste that in for everybody, so you can just cut and paste if you want to.
So I pasted the full command line in the Q&A window. For some reason, it's just highlighting the URL, but you should copy and paste the entire text, including starting from curl all the way to -xv.
All right. So there is that URL and the command line. Hopefully everybody can cut and paste that. I went ahead and ran that command line. What it did was pull down some of this code from an S3 bucket and uncompressed it. We can see that our file view has updated. There's a couple of folders. One contains information relating to some of the application workflows, and the other one is some operational scripts, things to create the table and import some bulk data. So we'll work through these steps quickly and go ahead with that. All right, in the core usage that we're going to have, the first thing we're going to do is actually create the table, our DynamoDB table. If we double click that, we can see up top here the script name. We can see the content of that script. So this is a Python script. It's going to use the Boto 3 SDK for AWS, and it's going to create a DynamoDB session. We're going to use a create table call to create that table for us. When we do that, we have to provide details about the primary key. In this case, that primary key is going to be composite, so it will have a partition key, which is used to do that horizontal sharding and scaling for us. And it's also going to have a sort key, which we use to collect up and store a number of different items that are related close to each other. So we define the data type for each of those, and then we say that these are the attributes in the item that we're going to require as a primary key. I'm going to create this table with 10 read capacity units and 10 write capacity units, just so that we can do these bulk operations pretty quickly. So I'll go ahead and run that. And down below in our runtime output window, we can see that the table was created successfully. The next thing that we're going to do is bulk load some example data into the table so we can work with it and try out some of these other application processes. The script that we'll use to load that information in is bulk load table. And the data we're going to import is in this file called items.json. It's about 210 kilobytes of items. In fact, we can see these are just one JSON object per item, where we definitely need to define our PK and SK values for the attributes because they're required. And the combination of the partition key and the sort key needs to be unique. in our table. So let's go ahead and run the bulk load script. We can see it's going to spin and work for a little while at 210 kilobytes of data. Maybe I think there's around about 900 items in there. It's probably going to take a little time, but there it is. It's complete. And the next thing we're going to do is run a script that will demonstrate the use of these collections and the ability that we have with a DynamoDB query API to retrieve multiple different item types about a particular collection or entity types in a single request. Because we've built in some prefixes and stored them all together in a collection, we now have the ability to make a call and retrieve multiple different items, multiple different types of items that are related in a single request. So the script we're going to use is fetch user and photos. In this case, we want to retrieve the item for a user, which is the metadata, the information about the user profile themselves. We're also going to retrieve some of the photo records, or all of them actually, that are owned or created by that user. So let's take a look at that script. I'm going to close out a couple of these. The bulk load is now complete. So for the sake of our example, we're actually going to hard code a particular user in here, and we're going to say for user ID Jackson Jason, we want to fetch the user record and the photos associated with that user. You can see that we're going to use the query API. We have to provide the name of the table that we're going to use. We specify a value for the partition key, which we must do because we're essentially saying, I want you to look in this collection, and then we're going to set a key condition on the sort key. And we're going to say we want those sort key values to be between a couple of different values. And these are variables in our key condition expression. After that, we have to actually provide the values that we want DynamoDB to substitute in to that key condition expression. So we can see that for the partition key, we're going to build the actual value of the user. We're going to add that user hash prefix and then concatenate Jackson Jason. And then for the sort key range, we want to say we want to get everything between a value that has this particular metadata value and anything that is after photos. And the way we've done the string character, which is directly after a hash when sorting according to ASCII. So in doing this, we're able to retrieve multiple different item types. They'll come back in sorted order, and we have a choice about the order or the direction of the ordering or the sorting. We can specify we want them back in forward sorted order or reverse. So we have the option to do that within a single index. With every query we make with DynamoDB, we can mix and match and switch between the sort direction as we need to. When we get the list of items back, we're going to, because we know that the user metadata will be first, we're going to grab that first item, and we know that it's going to be the user metadata, and then we're going to build an array of the different photo entries. Finally, we'll print those out and give this a run and just see how that goes. All right. So it came back as expected and gave us the metadata, the actual user profile information about user Jackson Jason. We can see the regular full name, which was stored in that record, and then we can see the time-sorted list of photos that have been uploaded by this particular user. So we have a lot of flexibility with that query call to make very directed queries against our collections. And this is a very efficient way to build these filters. DynamoDB gives us the ability to additionally add a second filter expression, which can be applied not just on the sort key, but against any other attribute. However, we have to read the entire set of items from the collection, and then we apply the filter before we return it to you. So the actual read consumption using a filter expression consumes or is associated with the full set of items that come back from our key condition expression. We want to do the bulk of our filtering using the partition key or a key condition expression on that sort key. And then maybe after that we can apply a filter expression which further eliminates a smaller portion of the potential matches. Okay, so moving along, we should look a little bit more. Now we have essentially looked at satisfying some of those access patterns that we had, some of the primary ones. We can create a user profile. That's pretty simple. We're just going to add a record. We can update that user profile. We can get the user profile. We can upload a photo. So we would just add another item into that particular user's collection. We can view the photos for the user as we demonstrated here with this particular script. And we can also view friends for a user. It would be a similar type of query as we use to look at the photos for that particular user. So we should move a little bit further along and talk about maybe some of the more complex queries and how we can satisfy them. In this case, we're actually going to build a secondary index which will be inverted. It's going to give us the ability to take what was the partition key in our base table in that primary index and turn it into the sort key in our secondary index. And the sort key from our base table will become the partition key in the secondary index. Did I get that right? I think so. It allows us to make a query coming back the opposite direction effectively. So we're going to go ahead and create that. Again, we're going to use one of our scripts here. It's called add inverted index. We can take a look at that script and get an idea for what it's doing. Again, we're going to use a DynamoDB client with the Boto 3 SDK. We're going to use the update table API, which allows us to change some of the settings for the table. In this case, what we're changing is that we're adding an additional secondary index. We can see that the global secondary index that we're going to create here is going to be called inverted index. We define the data types for the keys that we're going to use as part of our primary key for the index, or the index key. And we're also getting a choice here about which attributes we want to project. So that's a powerful option that we have with our secondary indexes. We can decide that maybe there are some attributes we don't need to satisfy the requirements for the query that we're creating the index to fulfill. So we can just project the attributes that we are interested in. That can be a nice efficiency when projecting only what you need. We're going to define the read and write throughput for that index, and that should go ahead. That should do it. So one thing that's interesting about DynamoDB's global secondary indexes is that they provide online indexing. So we already have a table. We have a bunch of data in there. We can add a secondary index, as we'll see here. I'm going to go ahead and run that. And we can see that it came back and says the table was updated successfully. So the table definition has been updated to add a secondary index, a global secondary index. What DynamoDB is doing now in the background is it's going in and building that index for us. We have to kind of backfill it based on all of the data that's already in our primary index in the base table. So it takes a little bit of time. We're going to let that run for a bit. The primary thing that determines how long building that index will take is the write capacity that we created the index with. So that will take a little bit. We'll let it work on that for a while, and then we'll come back and be able to check on that index, see if we can make some queries against it. So I'm going to use the opportunity, I think, to go back to answer some questions, perhaps, while we're waiting on that.
Sure, Pete. And if you can filter your questions by the ones that are assigned to you.
Sure. I think I can see those, the ones that you've assigned to me. Next one we have here is what does a schema migration process look like if you've iterated on your design and you require the structure of the old collections to change? So that's a really good question. I know that I think for a lot of folks, they have an expectation that, particularly when they've made changes to schema in a relational database, they're able to do that, and the database will kind of go through and change that for all of the records. One thing that that can create is actually an operational impact. So if you have a really, really large data set, going and making those schema changes can be very hard on the database itself. In DynamoDB context, we have everything already pre-built essentially, and so we need to go back and because the schema is flexible, we want to use that data a different way. And there's a number of different ways this can happen. One option would be maybe we want to start actually using additional attributes in each of our records. And the nice thing is, of course, with DynamoDB, it's schema flexible. We can just start as we update or write new records in there, adding additional attributes, and that can work really well. One approach would be, maybe within the application, rather than, and in that situation, we could go back and actually try to rewrite every single item in our table. We might have millions or billions of those items. Do we really need to do that, though? Maybe we're adding a new attribute which has kind of a default value. In our application, we could assume that default value. So when we read an item, if we don't see that attribute, we assume that it's there with the default value. But from that point on, whenever we're writing an item, we actually write and include that attribute in the written record. So that would be one approach. If you have a need to add a particular attribute that has a calculated value that's specific to that particular record, a very common pattern would be to use something like EMR, and use Hadoop to basically make this change across every record in your DynamoDB table by scanning it, reading one record, calculating what the new view should be, and writing it back. And I think while that is something that can take some effort and will consume some write capacity and read capacity too, the nice thing about this is that we do have that horizontal scalability of DynamoDB, so we can actually make use of something that can be massively parallel, like Hadoop, to do that as quickly as we need to, and we can scale up our read and write capacity as we need to just for this process. So that would be a few of the common approaches, I guess, to making these kinds of changes. Of course, if the change is really just adding a new index, we can add the GSI, and DynamoDB will backfill it and build that index for us in the background. Really depends whether you're actually adding attributes and how you need to use those. All right, let me answer one more question. There's a question here about, can we share AWS best practices for DynamoDB data modeler? And I'm not sure if that means specific to good practices for using the new Workbench tool, or just in general good practices about data modeling. We are going to have some future sessions where we'll dive into this in a lot more detail. We'll look at some really advanced data modeling and some best practices there, and we'll make a lot more use of the workbench to demonstrate that. So hopefully you'll be able to join those with us. Otherwise, there's a number of really great pre-recorded sessions that came from various reInvents over the years. I know that my friend Rick has an advanced data modeling session that he does every year at DynamoDB, and that's really pretty amazing. I'd highly recommend it if you want to go take a look at the recording. All right, I am going back to sharing my screen. I'm going to take a look at that index. So hopefully that is complete. What we're going to use that index for is basically making a query into that inverted index and finding a photo's reactions. So we're going to use a script that is called fetch photo and reactions. Again, we're making use of collections here and the ability to bring back a couple of different entity types here. We want to get the information about the photo itself, and we want to get the list of reactions. So that script that we're going to use is called fetch photo and reactions. And clean up after myself a little bit here. Hopefully the pace is okay. I hope everybody's able to follow along with us. Unfortunately, we lost a little time due to my technical difficulties, but please let us know if we're moving too quickly. If you have any questions, add those in the chat. So here's our script that very similar to the other query we made. We're going to actually bring back a couple of different types of entities. First, the metadata record itself, and then a list of related items. Here we can see we're going to open a connection to DynamoDB. We're going to hard code a user and a timestamp. We're actually using the timestamp to uniquely identify each photo upload. And our function here is going to use the query API. It's going to use the quick photos table name, which we had before. In this case, we're adding the index name. So we're telling DynamoDB, when we make this query, we want you to use this secondary index. Here is our key condition expression, where again, we're going to specify the name of a collection. In this case, it's the sort key from the base table, so it's still called SK, but it's being used as the partition key for the secondary index. And then in the rest of our key condition, we're setting a range. We want the sort key values to be between reactions and user. These variables, again, we'll fill in with some actual values down here based on the username and the timestamp. So we're going to specify for this particular photo, I want to get the information about the photo itself, and I also want to get some of the reaction information. And we're going to sort those in forward order. So let's go ahead and run that one. We can see the output has completed here. We can see the information about the photo itself, the user who created that photo, and the unique ID of that photo, which is a timestamp as it happens. Then we have our list of reactions to that photo. We can see the user who reacted, the photo that they reacted to, and then the particular kind of reaction. So we have a couple of smiles here, and 3 +1s or thumbs up. So again, we're able to use this to make some fairly complex filters around our collection and bring back a couple of different types of entities in a single request. So this is what we want to optimize with DynamoDB. Usually people using DynamoDB are wanting low latency. They want a really nice user experience. And in doing it this way, we can make a single request and get back all of the details we need, rather than going out and making a request to get the user and then going and getting something else and kind of making multiple network round trips. So that was great. Our Our index helped us out there. We were able to query the data a different way. The next thing we want to do is, again, we'll use this inverted index. Well, actually, we're going to, the same inverted index to find followed users. This script will be find following for user. So we can see here, we're going to create the connection to DynamoDB. We're going to use the username of Harold Watkins. And we're going to find all of the users or the friends that Harold Watkins is following. So we'll use that index again to be able to query those particular collections of friends for or followed records. We're going to use the table name as quick photos and index name inverted index. We're going to name the key condition, so that sort key value actually names the collection as Harold Watkins's set of friends. And in this case, our key condition expression does not specify a condition or a pattern or a range on the actual sort key for this index. So when we do that, we're going to get back all of the records. Again, we're going to retrieve those in forward sorted order. So we'll go ahead and run that. And we can see that we have found all of the users that are followed by Harold Watkins. And they're all listed here with a friendship record and the name of those users. And here we can see Harold Watkins is listed. So that's great. We can make use of our inverted index. One thing that's kind of interesting is that the information it's bringing back is not necessarily everything we want to know about these particular friendship records. We're getting their username, but we're not getting their full name or any of the other details about them. And so we could try, I think, in our data model to denormalize that, right? So each time we add a friendship, we add the details of that friend. You know, some of the information that's in their user profile, maybe their full name, their email address, those kinds of things. But we don't want to necessarily denormalize everything, because if we think about it, if one of these friends, maybe Natasha87, then updated the email address associated with their user profile, we would then have to go back and propagate that change through all of the records and other friends that Natasha has. So we might not want to do that. Maybe what we want to do is choose not to denormalize that particular information. We're going to use this pattern, but we're going to use another API called batch get, which will go and get the full record associated with each of these matches and decorate them with some more information. So let's take a look at an example of that. This particular script is called find and enrich following for a user. I'm just going to clean up after myself here. We can see if we take a look at this script. Firstly, we're going to get that list of following for user. We're actually going to make the query similarly to what we did in the prior script, the prior example. But we're going to retrieve the list of the results. We're then going to create a batch get item, which includes a request for each of those users, each of those entries, and we're going to get the user profile, the full information for each of those particular matches. Then we're going to bring those back using an array here and print them out. So this is a multi-request scenario. We're going to make one request, get the list of matching users, and then we're going to make another request, which is a batch request, to retrieve more information about each of those users. go ahead and run that. And there it is. So still really pretty quick. 2 requests, a couple of network round trips. We have our users followed by Harold Watkins listed out there as we did before, but now instead of just having the username, we can actually fill in their full name beside it. So one thing to learn from this, I think, is that we don't always want to denormalize everything. We want to denormalize where it makes sense and where it can help us to simplify and come up with a single item that we can make atomic actions against. We can get all of the information we want back in a single request. Sometimes, though, we don't necessarily want to choose to do that. It wouldn't make as much sense, and in that case, we can use this type of a solution where we will end up making a couple of requests, but they're still very, very simple and very highly performant requests that keeps our latency low for the overall application or the action within the application. All right. So a couple more requirements that we have here. The next one we want to do, and this is where we'll get into some transactions that I mentioned a little earlier. We want to be able to react to a photo. So that's going to be a write. And we want to be able to follow a friend. But we want to do this somewhat conditionally. We have some requirements that need to be met if we're going to react to a photo or follow a friend. For these particular patterns, when we want to react to a photo, we need to do a few different things, a number of actions, I guess, that we're going to wrap inside of a transaction. The first thing we're going to do is we have to confirm that the user has not already used this type of reaction on this particular photo. Another requirement we have is to create a new reaction entity to store that reaction. And then we also want to update the information in the actual photo metadata so that we can display anytime someone looks at a photo, we can see the count of how many reactions of each type that particular photo has received. So it's a little bit more of a complex use case, but thankfully we have transactions and we can meet the requirements using a transact write items call. So the script that we're going to use for this is a add reaction script. Let's pull that one up and take a look because it's really pretty interesting to see how we construct these transactions. Again, we're going to start with our Boto3 SDK and build a DynamoDB client. We're going to hard code the reacting user, the reaction type, the photo user, so who owns the photo, and the timestamp of that photo. And here we have our function to add the reaction to the photo. We're going to build out our values here that we will use in our transact write items requests. And here we define the transaction itself. And we can have up to 25 different actions as part of a single transact write items call. The first one we're going to define is a put. So here we're going to say we want to add a record that shows a reaction for a particular photo, and we only want to add it if it doesn't already exist. So we can see that we're defining the table name as quick photos. The item is going to be defined by this particular reaction and this photo. We have the reaction is going to be recorded as the reacting user and reaction type, and there's our photo value. Also a timestamp. So we're going to create this record, but we're going to provide a condition expression on this. So we only want to create this record if the attribute doesn't already exist, and we'll use the sort key value because that actually tells us whether the record exists at all. So I only want to add this particular reaction if there isn't already reaction from the same user to the same photo and the same type of reaction. So that's our first action for our transaction. The next one is to update the count of reactions of a particular type for a photo. So in this update call, we're going to update the actual photo record itself, and we're going to set the reaction count to one value higher. We're going to increment it. So these two things are either going to both occur and succeed, or both will fail and be rolled back. This is the nice thing. This is the atomicity that transact write items call adds for us around conditions and things that need to be met for multiple items at the same time. Either both will fail or both will succeed. So let's give this one a try. I'm going to run this script. And we can see that it's succeeded. It says that we added the sunglasses reaction from Kennedy Heather. So that was on that particular photo. So one thing we should know is that we don't want to enable, if this was retried or if this user accidentally hit their mouse button twice, we don't want to keep incrementing that counter because it's basically the same reaction to the same photo from the same person. This is what the transaction is taking care of for us. If we were to run it again, we'll see that it actually failed. It says it could not add the reaction to the photo. And that's because we already had a record for that particular reaction. And because it's wrapped in a transaction, we also did not increment the count of reactions of that type. So that's a pretty powerful construct that we can use with transactions. Prior to these transactional APIs existing, it was certainly possible to create these kinds of workflows, but it was complex and things could fall out of sync. It's really, really nice now for developers to be able to meet these complex needs with a single API call and have it work really reliably. So let's move on to our last need that we need to meet. The last one that we talked about was to follow a user. So this is where we are going to basically for a single user, we want to check that the following user is not already following that requested user. We want to be able to create a friendship item or an entity to record the relationship. And we want to increment the follower count similarly to what we were doing for the reactions. So we want to bump up that count in the actual user record to show that they're being followed by one more person. So we want to also do the reverse. We want to increment the number of people that a particular user is following. So these are a number of different requirements. Again, we're going to make use of transact write items to achieve that. And the script that we've got for demonstrating that is called followuser.py. Again, we will hard code some followed user and following user records. And we can see that we're going to create some of the information we need about these records and setting some variables. Then we're going to define our transactional actions, our items that will be a part of this transact write item calls that we're going to make. We have a put action, which is where we're going to put a new item, and we're going to condition that on saying that we only want to put this if the record doesn't already exist. This is what creates the friendship relationship for us. The next thing that we want to do is update the number of followers on the user that is being followed. And again, similarly to the previous one where we were counting the number of reactions on a photo, we're going to increment that followers attribute. And finally, we want to update the friend and change the number of users that they're following or friends that they're following also by incrementing. So in this case, we have 3 different actions that are part of our transaction. We want them to either all succeed or all fail. We can go ahead and run that. See what happens. We can see that it succeeded. User John42 is now following T. Martinez. And similar to the last example, if we try to run that again, it's going to fail. It's going to say that the transaction was canceled, and the reason is that some of the condition checks did not succeed. So we tried to add the same relationship again, found that the record already existed, and so that failed. That caused the rest of the transaction to fail also, which is good because we don't want to increment those counters if we're not adding a new friendship. So that really covers the last of the access patterns that we wanted to dig into and cover. Obviously, this is a kind of a simplified scenario, a particular use case. There might be some other application actions and activities that we need to support. But this gives you an example of some of what we can achieve using DynamoDB collections, having multiple entity types in a single collection in the same index. Demonstrates use of global secondary indexes. Then we can add them and remove them as we need to satisfy new access patterns. And it also shows what we can do using these new transactional APIs. They're really quite powerful and I think actually kind of fun to play with when it comes to building applications around DynamoDB data models. So let's make sure that we do clean up. I want to make sure that we don't forget about any of these resources. The first thing that we want to do is use this delete table script. We'll delete our DynamoDB table and the secondary index along with it. So let's go ahead and run that. And there we go. It says the table was deleted successfully. That's good. We don't want to leave that lying around. And then finally, we're going to get rid of our Cloud9 environment here because we won't be needing that anymore. Just go ahead and hit delete. It's going to want me to confirm that by typing in delete in the console. So we'll go ahead and do that. All right. So I think that's the end of the workshop. I had to hurry it up a little bit. I hope people were able to keep up. We've moved through each of these. We've done our cleanup. I think we will just switch back to answering a few questions. All right. Let me try to get to a few of them. Are there any in particular, Si-Young, you think I should try to get to quickly?
Sure. One of the questions were, is it possible to enforce relationships like foreign keys in two DynamoDB tables?
So that you could do using a transaction. So you could set a particular requirement for one particular item in one table. One of the actions that we did not actually talk about in the examples was a condition check. So you can make a transact write items call where one of the actions is not actually a put or an update. It's not trying to write something. It's actually just going to read another item that could be in a different table, and it's going to say, I want this item to appear a certain way. So you could certainly build some of those kinds of referential requirements using transactions. But in general, what you want to do is try to make use of those denormalizing patterns everywhere that you can to hopefully avoid some of that and simplify and keep everything that is related either in a single item or in a single collection.
There was another question on, does DynamoDB support writing business logic like stored procedures?
So I think the pattern that typically people would use for DynamoDB would be to turn on what we call streams. And streams is a Kinesis client library compatible log of any mutations that happen in the table. So it captures all inserts, all updates, and all deletes. And in that record in the stream is information about what the item looked like before the mutation and what it looks like after. So we can actually connect a process that reads from that stream and take some action as a result of that. You could write code in Python or whatever you want to do to take some action based on seeing a particular update. One really nice way to do that is actually to use a Lambda function just to keep everything completely serverless. You could take one of these Python scripts, use it as a Lambda function, and you can use that Lambda function as a trigger that comes off of that DynamoDB stream. So that's a really powerful construct, and we see a lot of customers using that. The great thing about that is, with Lambda, you don't have to manage any additional infrastructure. You basically just upload the function, you tell it to look at the mutation that occurred, and then you decide what you want to do based on seeing that change occur in the change data capture log.
I know for today's example, we used DynamoDB, even though we're using a relationship-based data model. When would you actually use something like Amazon Neptune instead?
So Neptune is really great. I think for me, where I really start to see that gray zone when you're choosing between the two, Neptune obviously supports graph models really, really well. It's awesome to be able to do some of those queries that will traverse multiple different edges and through multiple tiers of that graph. If you think about it in a DynamoDB context, we do sometimes build and support graph models, but just like in our example, actually, we ended up making one request, getting back a number of results, and then we had to go back and make another request based on those. So if you have maybe 3 or 4 or 5 tiers that you need to traverse, that's somewhere that DynamoDB could work pretty well for your particular needs. If you're getting beyond that, then Neptune basically allows you to make that a single query that then is run on the server, so it can do all of those traversals for you and then give you a result back. So in terms of overall latency, when you get beyond having to make a certain number of serial requests one after the other to do that traversal, that's where Neptune can really shine, I think.
Another question from Mike. If new attributes are added later to the main table, are they automatically projected to the secondary index?
Yeah, depending on what you set to project. The item in the base table is going to be projected into the secondary index as long as it has both the partition key and sort key attribute that you're using for the secondary index. So you can actually use that to build sparse indexes. That's a really powerful technique also. But when you define your projection into the global secondary index, if you were to say all, then every attribute in the base table's item will show up in the secondary index, even if you're adding new attributes that you haven't used in the table before. If you were to give a particular projection and name maybe 5 or 6 attribute names, then you would need to, and you add an attribute, you would not see the new attribute because it wasn't part of the projection. So I hope that answers the question. And the projection is something that you set when you create the global secondary index. If you wanted to change the projection, you can't do that on a secondary index that already exists. What you can do is create a new global secondary index with the different projection choice and move into that index and get rid of the old one. So I think we're really close to time here. See everybody's submitting their feedback. I appreciate that. Do we have time for one more question?
Let's try to do one more. How do you monitor the performance of DynamoDB API calls and tune them?
Yeah, great question. So one of the things that I really like that I think few people are aware of is most of these APIs, when you call DynamoDB, they give you an option that says, I want you to return how much capacity was consumed in making a response for this particular query. So when you're building this out, one of the things that you can do is turn that option on, run a query, and just see, how many write capacity units were consumed when I was writing or updating this record, how many read units were consumed when I made this query, and that can really guide you on how efficient your choices are in terms of what you're able to filter using a sort key condition versus what you're able to filter by adding a filter expression on top of that. So I highly recommend that. Another thing that you can do is, of course, keep an eye on your CloudWatch metrics, and you can see the maximum consumption. And when you look at that dimension in your CloudWatch metrics, that actually shows the most read or write units that were consumed in any single request during that time period. So that's really helpful too. That will tell you, for example, if maybe in your table where you mostly have lots of small items, maybe you have one item that's grown to be 200 kilobytes. So now every time I make a write to that, it's going to consume 200 write capacity units. You will see that in the CloudWatch metrics. I think we are actually out of time. So I'm sorry I lost a little time there. I had hoped to get to more of the questions, but hope this was helpful for folks. Definitely take a look at that code, maybe play around with transactions or go read up on those. And next week we're going to bring a lot of this together and build more of a complete application. That'll be the final session in this particular series. And we're looking at adding some more DynamoDB content that maybe digs even deeper into data modeling and using the workbench in the future. So be great to see some of you folks join us again for those.
Thanks, everyone.